Hello everybody. Today we talk about Poisson's equation. So what the relationship between Poisson's equation and Maxwell's equation? Maxwell's equation is used to describe the electric field and magnetic field, and we talk about magnetic field. It physically doesn't exist. It's a intermediate form, mathematical form of electric field according to special relativity theory. So what happened is electric field is in Maxwell equation is that its essential part. Well, actually it's a creation of Maxwell, right? The physics world, actually what we know is the energy exists in the space in terms of kinetic energy and the potential energy. And Einstein's equation enhanced that the definition of energy all the way to general relativity theory. So energy is the one we have to deal with. So from energy's viewpoint, entire Maxwell equation theory is summarized in Poisson's equations. That I tell you what it means here. So Poisson's equations approach is different from Maxwell's equation approach. Maxwell's equation has four fancy equations, the vector field. Poisson has only energy equation. Excuse me. And energy equation is going to be the basic of derive everything else, like electric field and magnetic field and everything else. Okay, so that's what we have here. It's just a different presentation of the nature, and Poisson's equation is in line with more physics law. The Maxwell law was a great inventions, but they can be all derived from one each other. Okay, so what is the potential energy when you have apple falling from the tree? Why it's falling? Because it's a potential energy. You have a height and weight, and the gravity weight, you bring this up to h height, you need the energy, you have to do the work, and this work is converted into kinetic energy and hit the ground, right? So potential energy is something that exists in the vacuum space, right? So when you have this conductor sphere and you have a charge q, and this is small q, if it's a positive and this is a positive, it's repel, you bring all the way back here and add it to this q, how much energy it takes, right? The coulombs tell you q r square. This is a force, and distance a from center, and you bring it all the way from infinity, right? Infinity, there's no force acting, so from that zero force acting state, you bring all the way back here. Okay, so this is defined as a force with a distance, and it's going to be negative k q r infinity a, right? So it's going to be k q a. Infinity is 0, so that's the potential energy at the A. Okay. So this the problem with this potential energy is same as gravity. When A becomes zero, it's called infinity, infinite energy, right? And this is a problem Einstein had. The the black hole is not actually the infinity. There are a lot of discussion about what's happened when A becomes small. But this phi A is our definition of potential energy. So when you have a potential energy, this is the potential energy at R from the charged conductor. And charged conductor, all the charge is on the surface, right? Because they repel each other. And if conductor, the charge cannot exist in the middle because they repel to the surface. Okay. And distance R. What is the electric field at the distance R, right? So that's going to be defined as vector field E. So vector field is created from Poisson's definition of potential energy. The energy, this is energy, slope of the energy define the force, because it's going to be, if you take a derivative of this guy, it's going to be R square Q, right? So that's a derivative. And for vector, in order to point right direction, this set the direction right, because this pointing this direction is I, right? So if you take a derivative of this, it's something like that, and I. So potential energy in this case actually we have to fix this sign, right? The force in this calculation, force is this way, and moving distance is this way, so it's a negative. So potential energy, if it's a positive, we have to put the negative here. So this is a potential energy. Potential energy goes this way for positive charge, right? Negative charge, it goes negative, means the force and the delta R is the same direction. Okay, so when you take a derivative, then you need a negative here. So negative cancelled out. So that's going to be the E. The E is pointing outward. So electric field times Q is a force, and it's pointing outward for positive, right? Okay, so fix the sign. When you calculate the this is not the gravity. The force is acting this way and you moving this way, So you multiply, it's a negative. So the potential energy is positive. This potential energy is positive. Potential energy is positive, and when you take a derivative, it's become negative. So you need negative sign. So we can invent electrical field as derivative of phi r. Okay. Now, since we have electric field on the surface of the conductors, we take a Gaussian law, right? So it's a 4 pi a square is a surface times rho is rho is the density of the charge on the surface. So divergent E equals this rho epsilon, right? Epsilon here is epsilon 0 and epsilon s. So this derivative of electric field is going to be the charge density. Okay, so divergent E equals phi r is going to be charge density epsilon. So we have equation here. Potential energy second derivative is going to be the charge density over epsilon. Okay, so this is the Poisson's equation. Potential energy. The potential energy, you take a second derivatives, you get charge distribution. And what does it mean? This is a location. So when you have the charge density distributed in a space somehow, then you can uniquely determine the potential energy. By what? By solving this differential equation. This is a differential equation. Second degree differential equation, right? So if you solve this equation, Poisson's equation, you can uniquely determine the potential energy in the space based on distribution of rho. Okay, so when the rho is given, the potential energy function is obtained. You take a derivative, you get electric field. So you can describe entire electric field based on distribution of charge, and that derived potential energy, and the potential energy give you electric field. So in order to have an electric field, you have a Gaussian laws, Maxwell's laws, but another way to do it is using Poisson's equation. And Poisson's equation tells you there is a unique relationship between potential energy in the space and the distribution of the charge. So this is a unique relationship between charge and the potential energy. From one, you can derive another. One direction is easier because potential energy is given, then you take a derivatives twice, then you get the you know how the charge is distributed in the field. The other direction is harder. you have a rho distribution of the charge, then you have to solve this differential equation with a boundary condition. Then you will get the potential energy. Once you get the potential energy, then you can have an electrical field. Now, that can be the end of story, but the math likes physicists invented another one. It's called vector potential. What is vector potential? Vector potential is, we want to find out the magnetic field too. So we define the vector field as rotational vector field become magnetic field. Okay. So we know rotation of B is J, the current, right? This is 0 S. So if you take a rotation of this, it's going to be rotation of vector potential, and this is going to be A, and this is B, and divergent of B is 0, so this becomes 0. So this is another Poisson's equation using potential vector. And what the potential vector does is to give magnetic field. By solving this you need a current, J vectors. So J vectors and potential vector is going to give this, because you can get the magnetic field by taking rotation, kind of derivative of potential vector. Okay, so equation is quite similar, right? Its only difference is scalar potential here and the charge here, vector potential and the current. So it's basically the same thing. It's just convenience of getting magnetic field, how magnetic field look like. This magnetic field is the artificial field defined mathematically, and when you want to know how it look like, you go through this vector potential equation. Okay, because magnetic field is the rotation of vector potential A. Okay, so this is the totality of Poisson's equation, and a lot of exercise can be created for you to do integral with boundary condition, the solving Poisson's equation, vector potential differential equation. This is the fun part. It's you can have next couple months doing various exercise for those. But important thing is to understand is why this kind of equation exists. The equation exists from the viewpoint of potential energy, and the vector energy is kind of weird. This is an artificial energy field. The physics vector is scalar. We call potential vector potential. This is purely artificial for artificial magnetic field. there's no such a thing like energy is a vector. Energy is a scalar in the physics. So Poisson's equation, the original equation, this is a straightforward equation, and the vector potential is like artificial field vectors, and it's act like Poisson's equation, just like Poisson's equation. It's for convenience. Whoever like math, they can manipulate the math and calculate the vector field. I mean, like a magnetic field. Okay, that's all for today. If you like this lecture, please subscribe and click like. Thank you.